So my name is Demetrius Sanas. I'm a affiliate of KITE, and my appointment is in the Department of Mechanical Engineering. I'm also the director of the Advanced Combustion Energy Systems Laboratory. I have the pleasure of introducing one of our stellar graduate students, Mahmoud Koraïem, today. We've worked together since January of 2020. This started out as maybe class coursework with Matthew Eisman and has since grown and expanded to include also contributions from Ioannis Nikiforakis, as well as I guess myself, and we've gone really deep on this. So today you will be learning about shrouded wind turbines, and not just about wind turbines. This is just maybe a way to evaluate different technical components, and specifically also looking not just from a performance benefit, but also the environmental impact that this may have, and also techno-economic analysis. You will hear today all sorts of interesting conclusions, which a lot of them had us scratching our heads, but they do make technical sense. So take it away.
Thank you so much, and thank you for having me. And well, I hope that we can find today's presentation a bit interesting and not dry. So let's get started. So this is basically a computational analysis framework, and we're trying to understand shrouded wind turbines, economics, and their performance, their impact on the environment, and from a slightly different perspective. Let's see basically what we're gonna do. Oh, wait. Is this working?
You might have to click on the PowerPoint window in order to have the mass place go to that window.
All right, thank you. So there's always the compulsory introduction about wind energy. Everyone knows that, but we have to do it. So we can see that for the past 20 years, wind energy has been taking the lion's share out of the renewable energy sources, whether in installed capacity or in energy generation. Of course, that's after the hydropower, and solar, as popular as it is, it's still kind of following behind, especially in the generation department. It has been led by breakthroughs in research in wind energy. So today we're going to discuss kind of an obscure-ish technology for wind energy, which is the shrouded wind turbines. So what is it exactly? We've got basically our regular turbine, and we put a shroud around it that looks like a diffuser. It creates a high pressure zone on the outer rim, and on the inside, it creates a low pressure zone due to the geometry, and it basically increases the airflow across the turbine. Okay, and we can parameterize that as a speed up ratio, which is the ratio of both speeds inside and outside. So what does that do? It increases the total kinetic energy of basically the wind going through the turbine, and in turn, we can get more power output out of the turbine. Okay.
I'm having trouble visualizing the shroud. Could you explain that again?
Think of it as basically a duct. You know the ducted fans?
Yeah.
It's basically the same principle or similar to it. And the shroud is basically just a disc that looks like a diffuser a little bit. So basically, when the air flows, it accelerates more through this part due to the low pressure. And that's basically what makes the turbine generate more power output. The idea was conceptualized in the 70s, 1978 to be exact, by Gilbert and Foreman. They conceptualized diffuser augmented wind turbine, where the shroud is basically a diffuser-shaped object. And they did an estimation of its economic viability. These numbers are in the current 2020 US dollars. So we have prices ranging from 14 cents per kilowatt hour to 46 cents per kilowatt hour. So that's a little bit on the higher end compared to current wind energy technology. It overlaps with some technologies for distributed energy, but it's a little bit on the higher end. Okay, doesn't sound that we can improve the cost by better implementation in the market, but let's see what happened after. What happened after is basically nothing. That technology remained mostly untouched until late 90s, where Philips et al., they basically created a prototype that's based on the K-Foreman designs, and they got a speed up ratio, what we discussed before, at around 2, and a power augmentation of almost 4. So the same turbine could generate around 4 times the power. It's very impressive. And we have more research by Grassman and Wang, and they have power augmentations that ranges between 1.44 to 2 or 2.2. In 2003, Oya and Abe, they conceptualized a different type of shroud. So this is what they call their flange diffuser. It's basically a diffuser with a flange in the end, pretty simple. And it could get a power augmentation of up to 4 to 5 times. Okay. And some improvements on that design. Toshimitsu, I butchered the name. He created a more compact version of that flanged diffuser shroud. So instead of the very long one, it's more compact, lighter, cheaper, and it has a power augmentation of 2.6. And there's more research that was done by other researchers in the area. And basically the conclusion is shrouded wind turbines, they're awesome. They generate a lot of power. Okay, so why don't we really see them around us everywhere? And this is what we're trying to answer. So it's a very impressive technology. But instead of just trying to get a $1 to kilowatt cost number and leave it at that, we're trying to delve in a little bit deep. We want to know exactly the effect of everything: the turbine cost and its performance, the shroud cost and its performance, the installation site, and the wind speed distribution. We're trying to find basically the effect of all of that together. So what we did is basically some sort of computational framework. The first thing we did, we wanted to kind of choose our own shroud. So we ran an optimization study computationally to basically determine an optimized shroud. And then we used LES and basically exhausted lots of Seawolf resources to find how that shroud operates under different wind speeds. And then we used the data from this shroud and we parameterized it in a way that allows us to basically calculate the annual energy generation of that shroud. And using the annual energy generation, we were able to calculate its economic viability and its environmental impact. So let's see what we did. First thing with the optimization, we created a parametric airfoil-based shroud. And then based on that shroud, we created a different shroud that actually looks like the Oya shroud, which is basically a shroud that exists in the literature. We wanted to compare them to see the benefits of each. So we used ANSYS for that. We created a parametric airfoil. Basically, it changes the camber, the maximum camber, the location of the maximum camber, and the thickness of the airfoil, the angle of attack. We threw that all of it in like a 10,000 design point configuration, and we ran it to see what is the best configuration possible. And then once we found an optimum configuration, we created a shroud that looks like it, exactly same proportions from Oya's literature, and we threw it in our LES model. And this is one we threw to Seawolf. We ran a lot of design points, different wind speeds, and in the end, we were able to parameterize that shroud basically as an augmentation. So we can translate the shroud into basically what it's going to do to the wind going through.
You explain the difference between RANS and LES.
Oh, okay. So it's basically just two different turbulence models. So in RANS, basically, it's Reynolds average Navier-Stokes equation. It's more of an averaged approach to turbulence. It's less computationally expensive, so it's actually very good for optimization studies like these. We ran a lot of design points. We ran them in 2D, and RANS was very efficient to get us the results that we needed. However, with LES, that's large eddy simulation, it's more of, it's a different technique to approach turbulence. We actually try to resolve all of the large eddies and just ignore the very small ones. And in doing so, we can actually find the effect of fluctuation of wind. If the wind crosses anything, it creates like turbulent eddies behind it. And we wanted to find the effect of these eddies on the performance. Does the performance actually, is it constant or does it change on the inside? So we needed to find that part. That's why we used LES for that one. Okay, so now for the LES model, we created a shroud. We put it in a 3D domain, boundary conditions of air going through different speeds. And we ran it for both shroud configurations. We ran it for flow speeds between 2 and 14 meters per second. And then we calculated K for all of the configurations that we had. And as we see here, we needed a base turbine for our work to see how that turbine is going to operate or augment it. So we used the AirX turbine. It's a commercially used turbine. It's actually a little bit old, but it didn't really matter as long as there's a turbine. We just need the comparative performance. So it doesn't matter if that turbine is not the best turbine. So we basically curve fitted all of their power and CP coefficient and the power coefficients and power curves as a function of the upstream wind speed. And that was basically the parameterization that we did for the turbine. And for the fluctuation of wind speeds, we used Rayleigh distribution. And this is basically Rayleigh distribution with different wind speeds. That work is actually courtesy of Mr. Yanis Nikiforakis here. Thank you. And basically, we used Rayleigh distribution to model what would wind speed fluctuation look like around the year to find this effect on the power generation. Okay, and this is basically how we calculated the annual energy generation. We took the wind speed distribution, so Rayleigh CDF. We took our parameterized power coefficient of the Bear turbine and the speed up of the shrouds. We combined them together and we were able to generate basically power coefficients, which is the equivalent of the efficiency of a turbine as a function of upstream wind speed and shroud speed up and the Bear turbine's power coefficient. We included that with wind discretized wind energy or wind power, basically the power in the wind that's allocated at each wind speed. We combined everything and we were able to calculate the energy in each bin. And using that, we were able to calculate the total energy that this turbine would generate in a year. Okay, and then we combined our annual energy generation with basically the total annual cost of the turbine and we calculated the levelized cost of electricity for it, as well as the lifetime environmental impact, and we were able to calculate the equivalent emissions. Okay, so let's look at the results that we got. First thing that we got from the optimization study, this is the effect of the thickness of the shroud. 10,000 design points is a lot of points. So after maybe like 4 months of running ANSYS, we got around through 2,500 design points, and we found that the effect of the thickness is quite negligible. Any impacts that we see here are actually just because the points were more biased towards here. The distribution of the points was not uniform through them, and we didn't find that running the extra 7,500 points for a whole year is gonna net us any extra results. So we decided to eliminate the thickness from our parameters. And these are the response surfaces, or actually they look a bit darker in PowerPoint, but basically these are response surfaces of the maximum camber location. They're actually more visible in on the screen here. The maximum camber location and the maximum camber and the angle of attack. And using these response surfaces, so we actually generated a lot of them, these are sample ones, we found an optimal shroud configuration that has a cross-section of NACA 9910 at an angle of attack of 15 degrees. Okay, and then we basically modeled a similar shroud based on the flange diffuser based on it. And we threw them in our LES model. And this is it? Oh, yeah. And basically, we can see that when we run it, there is a region of high speed across each of the shrouds. And this is basically where we put our turbine. Keep in mind that the location of this maximum speed is different based on each shroud. So we'll see that right now. Sorry, I think the
it's crashed.
That's unfortunate.
So cool.
Oh.
I'll just ask a question while it's spinning there. Are these turbines that are rotating to face into the wind, or are they static?
So the turbines would actually be placed inside of the shrouds, and the shroud itself acts as like basically the tail of the rotor to rotate it. But in this model, we didn't include the shroud because to do our economic analysis,
Didn't include the rotor.
we didn't include the rotor. Sorry, yeah, we didn't include the rotor in the model because the purpose of our model was not to actually determine the exact performance of the turbine, but rather the economic viability of it and the effect of stuff like shroud augmentation on it. So to parameterize our data, basically we had to run the shrouds empty because we needed to run a lot of design points just to get one number. And then we were going to see the effect of that number on the cost.
But generally speaking, these would be able to rotate in the field as opposed to being in a fixed direction.
Yes, and actually the shrouds help with that because basically the shroud, it generates a uniform pressure around all of its circumference. So when the wind blows on it, it automatically rotates the turbine to align it with the air, with the airflow.
And that wind speed data that you had was like hourly average data, or it feels like the time scale is important because I imagine there's some time scale of response for the turbine, and I don't know what kind of data you had.
So basically what we have is the annual fluctuation of wind speeds. So we don't care as much about the power fluctuation through an hour. To do the economic analysis, we actually need it throughout a longer span. And the longer span of wind energy is usually basically a year. That's how the cycle of climate works and how the cycle of wind fluctuation works. So our fluctuation is based all on a year. However, in our analysis here, because the time scale of this simulation, for example, is just 10 seconds. And so that would to give you a magnitude of how the wind speed fluctuates inside, and it fluctuates, I would say, thousands of times during these 10 seconds of runtime. So we average actually this data to find the augmentation or the powers, the wind speed up that we are looking for. I think it cracked. I think I have to run it again or something. Do I restart it?
So just while you're doing that, because I would imagine that the response is non-linear to the wind speed. So the average, the average, let's say you're sampling this distribution, it's like the average might be a certain value, but if that's comprised of equal parts low and very high, the average of the performance might not be the performance of the average. So I'm just trying to get the timescale for the data that you have.
Oh, I get what you mean. So actually what we found is at fluctuating wind speeds, when we make all of our data non-dimensional, the change is actually quite minimal.
Okay.
We can find that the shroud augmentation is, dare I say, irrespective of wind speed. There is some variation depending on the shroud design. Some shrouds act the same. Actually, we'll look at that part. Look at that part in the results right now. So that was one of the first things that we noticed when we were doing our results, because we didn't really know what to look for. We didn't know how is it going to end. We didn't have a template of or previous research on how it was going to work out. But basically, these are screenshots of the flow across the shrouds, and this is how we extracted the wind speed across the shroud. So we actually averaged it with respect to area along 100 points across the shroud, and we generated these curves for the wind speed across the shroud. So we found a very important find here is that the maximum point for each wind speed was dependent on the shroud type, not on the wind speed. So our maximum X was basically the same as long as you have the same shroud. And when we made our curves non-dimensional, we found that they almost overlap with very slight variation. There was more variation in the shrouded and in the flange diffuser one, the white oil one, but the airfoil one was actually quite consistent with the augmentation with wind speeds. So that was pretty interesting, because now we could translate a shroud into a number, which is basically how much are we augmenting our wind speeds. And that was the beauty of it. We don't really have to look at shroud designs. We can look at just one number, and then we can discuss everything in respect to that number. And these are the data that we found for these shrouds, the mean and the maximum and the minimum and standard deviation of our speed up factors for each shroud design. Then we looked to our turbine. So this is the power coefficient curves, and this is the bare air X turbine. And we found that there is a drastic increase in power coefficient, which is fantastic, right? However, we found something that's quite interesting, is that the maximum kind of drifted a little bit at lower wind speeds, which is it makes sense, because we make that turbine run at a faster local wind speed. So it will get it to its maximum point at an overall upstream wind speed that's lower, right? So instead of having the maximum at maybe 8 meters per second, we have it right here at 6.1 and 6.5 meters per second. Okay.
Can I ask a naive question? But naively, I think as the wind speed got faster and faster and faster, the power coefficient. What is the power coefficient, I guess, is my.
Oh, so it is the equivalent of the efficiency of a turbine. So basically, you can think of it as a performance curve. It goes to a maximum at a certain point, and as you go past that speed, it goes down. So this is true for that type of turbine. It's what is called a stalled control turbine. It basically means that this turbine has no means of controlling it. You just put it there, and you plug it into your load, and it turns at a constant speed based on whatever gearbox you have attached to it. And based on that load that's attached to it and its rotational speed, it's going to run optimally between a certain range of wind speeds. You put it at a faster speed, it's not going to run as well, because basically the design of the airfoil of the blades of the turbine itself is not designed to run at that speed. If you run at a too low speed, it's not going to run as well. So you need basically to bound it between wind speed range. And what we found here is the wind speed range for that operation is actually a little bit tighter. If you superimpose both curves, you'll find that the shrouded turbine has a slightly tighter operating range, but it has a much higher power coefficient.
So how do you compute the power?
That's what we're gonna do in the next slide. So basically the power is calculated by multiplying your power coefficient times the wind power that's incident on the turbine. And when we did that, we found something quite interesting. Because basically what we did is when you put a shroud and when you put it in a wind tunnel based on the previous research work, then you run the wind tunnel usually at a constant speed, maybe 6 meters per second. Okay, you get your results at 6 meters per second. We have around 40 watts for the bare turbine, and we have 110 watts for the shrouded turbines. We find impressive results. We say hooray, and we celebrate. And what happens is when you run it in a wind tunnel, usually your wind tunnel has a constant speed. What you do is actually you change the load on your turbine. And when you change your load on the turbine, you change the turbine speed. So it acts as if you're changing the wind speed, but in realistically, you're not, you're just changing the load. So you're shifting a little bit across that line, but the incident wind energy is the same. But what happens is when you put the turbine outside, and you basically measure the whole spectrum of wind speeds, then you'll find something peculiar, is that your available wind energy goes down when you go at lower wind speeds. And it goes up when you go at higher wind speeds. But when you superimpose that with your power coefficient, then you'll find that at higher wind speeds, the increase in power coefficient, the increase in available wind speed is actually offset by a much lower power coefficient at high speeds. Remember, that turbine is designed to run at lower speeds. So when you try to run it at a higher speed, you don't really benefit from the efficiency of that turbine. It's like basically running, idling your car the whole day. You're not really using too much power, but you're gonna lose gas. You're running at a very low efficiency of sort, right? Okay, so then we combined it with the annual available energy. And here we found that shrouded turbines actually can generate a little bit higher annual energy generation. These are not the upstream wind speeds, these are the site average wind speeds. So now the speeds in the x-axis, they're not upstream wind speeds, this is the average wind speed across the whole year. And we found that they generate more energy, basically up to maybe 7-8 meters per second, but past 8 meters per second, your energy generation dwindles. And the regular turbine is actually better. That was quite interesting. Okay, we calculated the power output of the turbine, and here we can see the effect of the annual fluctuation of wind speeds. So this is the rated power of that turbine, and this is the power that it generates throughout the year. And we can actually translate that into some sort of capacity factor for the turbine. But basically, this shows the effect of having your turbine throughout the whole year. If I have 150 watts turbine, doesn't mean it's going to generate 150 watts throughout the year. It's going to generate much less than that based on the wind speed fluctuation. Okay, levelized electricity. And this is when we found the biggest shock. This is the bare turbine. It has the lowest levelized cost of electricity, 6 meters per second and up. So basically what we did is we spent money, we wasted research only to find a turbine. Oh, and I forgot to mention, so these are 5 turbine configurations, the steel brim diffuser, that's the OYA 1, aluminum brim diffuser, OYA 1 made out of aluminum, and then fiberglass airfoil, carbon fiber airfoil, and aluminum airfoil, comparing basically different materials and combining different materials with different designs. And here we found that only the steel brimmed diffuser and the fiberglass diffuser, they were a little bit better than the regular turbine at maybe wind speeds of 5 meters per second.
So maybe you'll show this later, but I don't have a sense for what average wind speed is across the US. Like, are there big chunks of the US that would fall below this 6 meters per second, and chunks of the US where it would be above?
So usually, if we're talking about a site for wind speeds for onshore, we're talking about a site wind of 8 meters per second and up in average wind speed. So when we say that a site wind speed of 5 meters per second, we're talking about more of a residential area or an area that doesn't get a lot of wind. But then will come a question, okay, so some configurations of these turbines can work at very low wind speeds, but what's the cost? It's around 50 cents per kilowatt hour. You're better off putting solar on your roof, right? Because in the end, we're comparing money to money. We can make it work better than the turbine, but why even go wind at that point? So if we want to make wind energy work at a low wind speed like this, like a price that maybe is sub 20 cents, right? Okay, so first we looked at the environmental impact. And with the environmental impact, we learned that aluminum is a no-no. Okay, we found that the cumulative energy demand, global warming potential, acidification and eutrophication potentials, the aluminum was very bad across all boards. We found that the steel diffuser and the fiberglass and the carbon fiber airfoil ones, they were the ones that were quite acceptable. And we did the same thing as the levelized cost of electricity. And we calculated all of these curves across site average wind speeds. And we found that they actually work pretty well at similar wind speeds. So at this point, we kind of got the idea. Something is making these turbines not work as well at certain wind speeds, and we need to figure out why or what. So we decided to experiment a little bit. First thing we did is, since we parameterized everything, we decided to use cheaper shrouds. And we found that by using cheaper shrouds, all of our shroud costs basically were reduced by 50%. We found that their curves kind of like linearly shifted downwards, but still no apparent improvement over the IACS. You have to make the shrouds so cheap to the point that they are almost the same cost of a shrouded wind turbine, of a bare wind turbine, and even at that point, you'll be basically almost at the same point. Maybe you can get up to 10 meters per second, but that would be like with magic shrouds that you asked your genie to get, not ones that we pay money for. Okay. Second thing, we decided to test increasing the speed up ratio, right? We said that shrouds are better the higher the wind speed increases, right? So we did that. We found that for a speed up ratio of 2, instead of like 1.4, 1.5, we had a dramatic increase in CP. However, the curve tightened even more. So when we calculated the power output, we were still stuck with the same power output of around 152. Only thing that we had is a slightly tighter curve. So how does that affect our cost? We calculated the annual energy, and then we calculated our LCOE, and we found that in making the curves a little bit tighter, it allowed for a higher region of viability. So now with a higher increased speed up, we can make these turbines a little bit more viable at even lower wind speeds, but still sub 5 meters per second. And the costs didn't improve, still almost within the same range. Okay, so we tested something else. We tested what if our turbine had, the base turbine had a higher CP with a 50% increase in CP. And we found basically that the same curves here just scaled up, and the same happens with the costs. So nothing much.
Could you define the CP?
Sure. That's the power coefficient of the base turbine, the power coefficient of the turbine. So basically, when we use a more efficient turbine as the base turbine to augment, we found that yes, it makes the turbine more viable, the shrouded ones and the bare one, but it still doesn't make the shrouded turbines better than the bare turbine. So we tested one last thing, and that's the existing energy range. So we discussed that our turbine was basically a stall control turbine. It behaves the same under constant wind speed as long as its speed is constant. So we decided to use a hypothetical turbine that has double the operating range. Okay, and in doing so, we still found our output to be equivalent because of the phenomena that we discussed before. However, when we looked at our costs, something beautiful happened. We found that since the shrouded turbines had a higher range of operation, now we can use them for up to 12 meters per second. Pretty good. And at a sub 10 meters, at a cost that's less than 10 cents per kilowatt hour, which is pretty impressive. Okay, that's very good. Now we're getting somewhere. So we decided to combine two effects. We basically called it like the improved turbine. We decided to test it with a 10% increase in speed up and a double of the operating range. And suffice to say, we got pretty good results here of up to 8 meters per second or 9 meters per second at a sub 20 cents LCOE. Pretty good, pretty good. So now we can see that it can be quite competitive, but we wanted to get the answer for sure. So are shrouded turbines the way to go? And then we had to remember, we don't have to augment turbine A to make it work. What if there's a turbine B that I can buy off the market? So we got turbine B. Swift's turbine is a turbine that costs almost the same amount of money that you pay for a shrouded AirX. And we did the same thing to the Swift turbine. We compared them. When we look at the CP curves, actually the Swift turbine has an almost equivalent CP to the AirX, except for it's a little bit higher at the end. The power curve actually shows that slight increase here. Here we find better turbine control system. That's basically what makes the power increase at higher wind speeds. And we generated the annual energy, we calculated the annual energy generation. Swift turbine beat the shrouded turbines across all the boards. But what matters is actually the cost. So we looked here and we found that, yeah, shrouded turbines were a little bit better than the Swift, up to 5-6 meters per second. The same story that we're working with, and this is the improved turbine. But the Swift was still better across all the boards. So what did we conclude from all of that? Is that shrouded turbines, you put them in a wind tunnel and you'll get impressive results. But if you put it outside and try to calculate how much money did you spend on it in a year, you're better off using a different type of turbine, unless you are in the very narrow category of like maybe 5 meters per second average wind speed or less. But at that point, why even bother with a wind turbine? You're better off using solar, you're better off using a different type of technology, you're better, I don't know, saving up and getting a more efficient car, right? So that's basically what we concluded. These are the summary of the data from the Swift turbine. And this is basically our framework, all of the analysis procedures. And I'd like to thank you so much for your attention and for your time. And I'll answer the question first. But I just wanted to thank first Convert CFD. They provided us with the licenses of the software that we used. I'd like to thank IACS for first hosting me here, and more importantly for giving me access to Seawolf. We used it a lot, sometimes too much, and maybe thank you and sorry for that. And I'd like to thank the Department of Mechanical Engineering for funding our research. And thanks again. All right, I'll take your questions.
There's no need to feel guilty about using too much computers.
That's good to know.
You talked about environmental costs, but not the issue of bird strikes. And I'm just wondering whether you have a sense for whether the shrouded designs are more or less prone to bird strikes.
That's a very good question. So the answer is there is actually no data yet, because no one fielded shrouded turbines in an area where there are birds to actually test what would happen with more installation of them. However, shrouded turbines usually are on the smaller side. So if you have a satellite dish on top of your house, it could be equivalent to the size of a shrouded turbine, if that would be like a factor. However, there was research done on the noise generated of shrouded turbines. And the pressure differential between the outer part of the shroud and the inner actually causes a bit more noise. So if you put a wind turbine on a farm and it's noisy, the shrouded variant will be a little bit noisier.
So just to follow up, I think the size is not so much an issue, but I do think that the pressure, I think the question is whether it's sucking bats and birds into it that don't have the flying capability of avoiding it, and also the frequency of the sound. So those would be the things. But if you could show that even a modest improvement in bird strike potential would allay a lot of fears and might be more likely to be built even at lower efficiency, which is to say the efficiency of a turbine you can't get permits to build is 0. And that might be its big selling point if in fact it turns out to be even 10 or 20% safer for birds.
That would be one way to look at it. However, if I'm gonna basically do a back of envelope calculation and we're just thinking through my head, if we have a pressure suction zone, then anything that's not strong enough to fly is going to go through. And so I would say it's going to be worse for the birds, not better for the birds. But the question here is, and that's the point of the research, is it worth answering that question? Because to answer that question, we have to do research, computational time, money, and then in the end, is the product worth it? It's not like I have a technology that's going to save us thousands of billions of dollars a year, and then we're trying to find a way to justify it environmentally. We actually see that it doesn't work as well. So I would say I don't think it's worth investigating unless, well, actually, so there is that point. We're still talking about a stall control turbine. So maybe a turbine with a more improved control system can operate better. It can take benefit of that increased wind speed without suffering the issues of the contraction of its operating range. If I would invite anyone to try to answer that question from an economic point, and if it works, then we can try to see, okay, how can we make it safer for birds? But I think maybe the question for the birds is a little bit too early to ask.
I would just say that I think that you might be able to justify a less efficient turbine that was safer for birds. So I don't think it actually has to be a better turbine. For it to be a better.
I get it now. I get it now. That would actually be one way to look at it. I think it's gonna be a little bit hard because I would say inherently, just by looking at it, it's gonna be as well for the birds. But maybe with future designs, maybe we can find a way to make it safer. Who knows?
So I don't understand how you computed the power coefficient without the turbine itself or computing the power. In fact, I can see that you have like a way too high power coefficient. I mean, you know, that's
Yeah, I know.
there's a
So
limit on
the best limit is actually based on the area of wind that's going through.
yeah.
So the way you calculate the power coefficient of a shrouded wind turbine, you actually calculate it for a larger area of wind speed of wind that's going through. So in theory, you're basically, it's like a combined power cycle. You're taking from the free. You don't have an input. Your input's actually larger just by the physics of it. So the best limit is actually based on a hypothetical turbine that acts as a basically just disk and pressure goes down across it.
Well, in the assumptions we do, it's actually take it as a streamline, so it would be very much like a shroud.
That's true, but the thing is, if you calculate the power coefficient of the turbine based on the area of the air that goes to the shroud, is what I'm trying to say, then yeah, in that point, you'll find a CP that's less than the best limit.
So the question, the real question, how do you compute the power coefficient?
That's the thing. You compute it the power coefficient is computed on based on the area of the turbine, because in reality, you don't actually know the size of the stream tube going to the turbine. In a shroud, in a regular turbine, you basically use your cross-sectional area of the turbine, your frontal area, as the area that you use to calculate your CP, right? The wind power going through.
I know what you did then.
But in a shrouded turbine, that area, you don't actually know the size of the area, and that's gonna change based on the augmentation of the turbine. So basically, the power coefficient still uses the same classical definition based on the frontal area of the turbine that will basically bypass the Betz limit. So that's how it bypasses it, because the classical definition of a Betz limit was based on a shrouded, on the frontal area of the turbine. It didn't account for having a mechanism that sucks more air in. In the end, the Betz limit is just, it's more, it's gonna be corny if I said it's a construct, but it is actually a construct based on a scenario that you.
I mean, it's the most optimal scenario. It's like Carnot cycle and.
Exactly, but it's an optimal scenario of sucking an area X through a turbine.
No, I understand that.
So that's the whole point is the area X itself. If the area X becomes
bigger.
it's a bigger area. So you're sucking a bigger area, but you're still calculating area X. However, if theoretically we can calculate the area Y that gets sucked into the turbine, then we'll find that the Betz limit is still respected.
You can do that.
You can do that, but it's going to be a case by case, because it's going to be based on whatever on the augmentation of the shroud itself. So each shroud will have a different type of area. You're going to have to use a different area for each turbine that you're using, even if it's the same turbine.
So my other question is, why didn't you include like a better disk in your runs optimization for the shroud?
So for that point, because we didn't know first where the actuation disk was going to be. And that's the issue. The shroud increases wind speed, but you don't know where it's going to increase it. For the Oya shroud, the optimum point was right here. But for the airfoil shroud, it was a little bit forward at around 0.2 of the port.
But my point is that it will slow down, you change the physics of that diffuser just because you having that slowdown in
The
there.
physics themselves don't change, but the variation in the number, they were about like 10 to 20% error.
It will change the physics because you have a slowdown, you will have a adverse pressure, you will have an adverse pressure gradient just behind your turbine. So it will completely change you will have detachment of the boundary layer over the airfoils.
That's true, and that's why the compact shrouds actually don't suffer that. That you suffer on longer shrouds. Because if on longer shroud and you put a turbine here, then you separate the boundary layer right after, and the rest of the shroud is different. But with compact shrouds, I mean, here the optimum point is at 0.4. With research that was done, like with Oya, for example, the difference between the location of the turbine and the performance of the shroud when they tested it with turbines, there wasn't that much variation. The variation was between 10 to 20%. But keep in mind, 10 to 20%, that's large if you want to calculate the performance of the turbine. But it's not large when you're doing economic analysis and environmental analysis. There's a lot of assumptions. I mean, the environmental data that you get, for example, there could be 50% variation between source and another just on the environmental impact of a certain material. And with the economic one, you do lots of assumptions as well. Even just using the Rayleigh distribution, that's an assumption. So when we calculate the variation by putting basically a disk in the middle and calculate the data, the variation in the results that we get actually 5% because it dissolves in the data that we get. More importantly, if we introduce an actuating disk in here, not an actual turbine to simplify the calculations, still don't know where to put it. So we'll have for each design point to put the actuator disk at a different point. And that could not even quadruple, but could even make the computational time increase by 10 times. And the thing that discouraged us from doing that is, as Professor Asanis mentioned, this research started as a class project. So the first run of data gave us an idea of what to expect. The first surprise was we found that it's not really that viable. So at that point, we wanted to prove that point and at the same time not consume a lot of computational data for it. I mean, we've been running simulations for more than a year. I don't think it's worth the effort to run it for 3 years instead of a year to get the same result, just with like a 5% variation or less.
Can you obtain the maximum pressure from the airfoil data?
Like the maximum pressure?
The pressure distribution of the airfoil.
We can, but we didn't really need to because we were basing our data on we have the 3D data. We can generate it if you want, but we don't really need to because we were actually dependent on the wind speed increase.
Yeah, I'm interested. Why do you include such a long range after the shroud? Is it actually affecting anything? Because how I understand it, you're interested in the region where the turbines they can be placed, and you're simulating a lot of like the eddies happening afterwards.
Oh, it's because we need to resolve all of our domain to actually get results here. So if I try to, for example, just run from this point to that point, I need to give my solver boundary conditions. That part has fluctuating flow, and I don't even know how the boundary condition there is going to look like. Actually, our domain is not even up to here. Our domain, our real domain, is up to there.
Okay, so if you would place an outlet like closer to the shroud, it would affect what's happening inside.
Yes, and our model actually wouldn't resolve the problem. So any data that we get there, we're going to find like pressure waves going back and forth. Our solver is going to oscillate. We're not going to actually get like proper results. That's why we need a larger domain. So our domain actually extends like maybe up to this point, and it's actually much higher. We're just taking a screenshot of the part inside of it.
How many cells do you have like, in the whole thing?
I would say 10 millions on average. It varied based on the wind speed because we were using adaptive mesh refinement. But it was around 10 millions for each cycle.
I'm just trying to understand the big picture a little bit. I don't know anything about wind turbines. So the reason the shroud was interesting is because it's going to increase the wind speed going through the turbine, right? So I'm having trouble understanding why when you put the shroud, the efficiency curve like shrinks in width. So like if it's just increasing all the wind speeds, no matter what speed you start with, it's just increasing the speed. Why does now like the operating range where it's efficient like shrink to only a little bit of wind speeds when before you added the shroud, it was efficient over like a wider range? Does that make sense?
Yes, so basically, I'll go back to the first slide for that. Actually, yeah. So basically, what we did is actually, and that's actually to answer part of your question as well. To calculate the power coefficient of a shrouded turbine, what we did is we used the actuating disk theory. It's basically a theory that assumes there's no turbine here, just basically a disk, and the pressure goes down as you go through that disk. That's basically what happens when going through the turbine. And based on the results of the experimental work by Oya, they found that the turbine actually operates the same based on the local wind speed incident on it, regardless of the shroud design. So when we combine both of those, we found that the turbine basically will operate based on the wind speed that's coming right here. So I'll try to show slide. I think there's a slide in the supplemental material that kind of simplifies that. Okay. So basically, when comparing a bare turbine and a shrouded turbine for them to generate the same amount of power, okay? Then they would have two different upstream wind speeds. Think of it from that perspective. So that turbine, let's say it has a power coefficient of 0.3, okay? And that one has a power coefficient hypothetically of 0.6. So that one can take half of that wind energy and still generate the same output, right? So in doing so, that means that this wind speed, the U infinity V, will be higher than U infinity S. Okay? And since the curve of the power coefficient is bound for a stalled control turbine, it's basically bound between two wind speeds. Okay? So that turbine that's running at a much lower wind speed, okay, if that wind speed became the same as the one up here, it's going to be much higher, right? So what will happen is you're basically multiplying your wind speed by a factor. And that factor will make the curve shrink. Think if you draw a curve.
You're not just shifting.
You're not just shifting, it's shifting and it's shrinking. So, and that shrinking factor is actually your speed up ratio. So if you have a wind speed up of 2, then your power coefficient curve is gonna shrink by half.
Okay.
If you have a speed up of 4, then your power coefficient curve is gonna shrink by 4 times. And it's gonna shrink and shift a little bit because it's gonna basically every point is gonna be multiplied by half or multiplied by quarter.
Thanks so much.
Oh, thank you. So that's basically what happens with it. Mm-hmm.
We were talking about noise earlier. Are you able to make a prediction about noise generation from these computational models just based on pressure differences within the system?
Yes, so we didn't do that, but if we have the 3D flow field and we have pressure there, so you can use Folk's equation to Folk's full Newton equation, and you can use that to process basically the noise. You can basically it can use the pressure gradient to generate noise output or in decibels. So that can be done with our pressure field. However, a more accurate representation of noise would have to model the turbine as well inside. Because we don't just need to know what noise you're gonna get by air going through the shroud, but the noise that you're gonna get from the turbine itself. I don't know which one is going to be higher. So I think that would be a question to be answered by a model with a turbine running in it.
I don't know if this is gonna make sense, but
Go ahead.
so for a turbine, it seems like since you're shrinking the efficiency curve, like you explained. So different shapes of turbines are more efficient at different wind speeds.
Yes.
Okay,
So
did you
each
add
turbine-
something like the flaps on airplanes to kind of like change the shape of the turbine depending on the wind speed? So now you have like a broad.
that is actually what they do. So that's basically pitch control. So on some turbines, you can control the angle of attack of the turbines themselves. And in doing so, you can actually make the turbine run better at higher wind speeds than turbines that can't shift their blade. Because what makes the turbine slow down when the wind speed, what basically makes it doesn't generate as much power is there is a difference between the rotational speed of the turbine and the air going in. Okay, so that difference causes some sort of relative velocity component. Okay, each turbine is optimized at a certain angle for that relative velocity. If that relative velocity angle is too much different from the angle of the blade, then that turbine will not generate power output expected of it. So that difference is very high at low wind speeds, and it's very high at high wind speeds. At your optimum point, they overlap. So what you do is if you can turn your turbine blades to align it with the relative velocity component based on your speed, then you can basically squeeze more out of your power generation curve. That's why you'll find that some turbines have more of a flat line at the end of their power generation curve instead of a slope going down. That's due to better control.
That's the last turbine that. So
Yeah.
if you combine that turbine with your shroud, do you get better?
You could get better turbines, but the question here, is it still worth it? We could get a turbine that generates more power output to a certain extent, but is it still economically worth it? Because we still have to factor in the cost of the shroud and all of the impacts coming from it. And that's what makes this problem a more complicated question to answer. It's not really a simple answer to a simple question. We have to explore lots of scenarios and see what makes it tick. So I would say that's maybe a recommendation for future research.
Yeah, you guys looked at a lot of different parameters and changing different things, so it was really cool.
Oh, thank you.
That's very thorough.
My question relates to the cool bit. I mean, it's that you optimize the shroud using the RAN simulation. So how did you parameterize that? Do you have a sense that you found a globally optimal shroud, or do you just try to do local optimization starting from some existing configurations?
Oh, so we use a parametric airfoil. So what we found is the best shroud that you can get out of a 4-digit NACA airfoil. So that's not the best shroud you can generate.
Okay, so I didn't understand that acronym, but that's referring to a specific shape of airfoil.
Exactly, a family of airfoils.
Okay.
Well, basically, and each of the digits it tells you what configuration of the airfoil, how thick it is, where is that curvature at, in the middle, at the end, how like deep is that bowl part. But in reality, we found that, so this is actually a screenshot of the optimal shroud, and it is actually quite similar in idea to the flange diffuser, where we have basically a very low angle of inclination in the beginning and then a sharp flange. And here that will actually address another part of your question about the separation. What makes this design work well is that very low angle reduces the potential of flow separation in the shroud. When flow separates in the shroud, it's not going to work. That's why the original design by K. Foreman actually had a slotted diffuser. So it was a diffuser with a larger angle of attack, but there are openings here. So that the air, the boundary layer keeps like getting regenerated instead of separating. But what Oya did in his design here, instead of using a diffuser that has a very large angle where the flow could separate and then basically cause disruption in the pressure, he used a diffuser with a very slow angle and then just a steep flange at the end. So that very low angle reduced the chances of flow separation, but still that steep flange in the end kept the pressure gradient across the shroud. So that's why even when you put a turbine, it still works almost the same way. If it was a diffuser with a very large opening or a very tall diffuser, then it would do that, it would separate. But yeah.
Yeah, I also think because you're using the original power curve, and I believe if you have this shroud, your original power curve will actually increase the efficiency of it because you don't have the bound vortex on the tip of the blades.
Come again?
You know that you're using the original CP curve for computing the
shrouded turbine CP.
Yeah. So the thing is that I believe that the fact that you have the turbine and the shroud, it will actually increase the efficiency of the turbine because you won't have this bound vortex that it's generated at the tip of the blade. So your blade will be, because at the very tip of the blade, the force,
Yeah, the tip vortex, yeah.
the force goes to zero basically.
Because there's nothing, there's just like a vortex that keeps bigger.
Yeah, so I think if you have that shroud, that efficiency will increase, and it might even be like better for your the point of
That is a possibility. However, based on the research of Oya, they found that the difference is marginal still. They basically found that the main effect that affects the CP curve, so they actually measured in their literature, they plotted the CP curves with the turbine when it's shrouded and unshrouded, and you'll find that both curves are actually almost the same. The only difference is they're just expanded, it's contracted like we've seen here. So what you'll find is any shrouded turbine, yeah, there are other effects, and even the blockage of the turbine itself, it affects everything. But all of these effects, they are minimal to the effect of the augmentation itself. So what you'll find is the curve will almost remain the same. It'll just get bigger or smaller. The only difference is the speed up ratio itself, it will change a little bit. So if you run the shroud empty and get a speed up ratio of 1.5, for example, and you put a turbine in it, you're not going to get exactly 1. You'll get maybe 1.6, 1.4. It depends on how fast the turbine is running and what design of the turbine you're using. But that will introduce other variables that can't go into an economic analysis. So for a performance analysis, actually what we do, actually I had an old runs where I had turbines in the shrouds. But using that for economic analysis is not going to make a point because it gives me data for 1 point. And I have to run the same data at different turbine operating points at different upstream air speeds as well. So I lose the parametration, the parametric effect that actually allows me to calculate the economic viability. So that's why this research, it's going in between. It's not a performance analysis research, and it's not a pure economic research. We're combining basically elements of both to get to answer a question. And then if we find that this answer tells us that, yeah, this turbine has promise, then we can go the whole performance route. And then we can put turbines in it and model all of the operating points of that turbine at different wind speeds and do the whole 9 yards. And if we find that it works, then we can take the whole economic route. We can go into what materials to use. Am I going to use here? The aluminum is bad, but that's because it's not aluminum. Recycled is better. So then I'll go to the path. Okay, let's use recycled aluminum. Let's use recycled carbon fiber. Then so we can explore both aspects of the work. But basically what we were trying to do is actually answer the question of, is it worth it to go with that route and the other or not?
Thank you very much, Dave.
No, thank you.